not often happens, but yeah, this time it's great. I appreciate the opportunity to present our studies that we've conducted over the last 10 to 15 years on soil erosion, BMP effectiveness, and computer modeling. So even though my name is on the first slide, it's actually a product of many other people that I worked with over the last 10, 15 years or so, including students, my colleagues in the department, as well as outside of the state. As we all know, soil erosion and sedimentation is a global issue. It's not unique or specific to Kansas. However, in Midwest, it's definitely exacerbated due to significant agricultural production. And Kansas is one of those states that's heavily in brown area, especially on the eastern side of the state. If we look at the National Resources Inventory by the USDA, that it's estimated over the last 20 plus years a steady soil erosion by water at about 2.67 or 2.5 tons per acre. And that value has not changed significantly since, again, the 90s, even though a lot of management and mitigation efforts were implemented during that time. In addition to that, also we can see that wind erosion also is a significant issue in the state, which is on par to soil erosion by water. Kansas is the second state estimated, according to that inventory, in the United States for the production of sediment from the upstream sources. Again, so the values are a little bit outdated. They're based on the empirical models that USDA is running called Russell. And some of the management practices in that model are used from the 80s and 90s. So with all the efforts, I would assume that in reality we have a little bit lower production of sediment estimations. Again, so those values are not accounted for non-sheet and rill erosion. So it's only erosion that's generated from the land in the upstream areas or uphill areas of the hill slope. So there is no gullies, there is no ephemeral channels, and there is no stream bank erosion included in those estimates. So if we are in a perfect natural stream condition, then when we look at any particular location along the stream, that we should see an equilibrium. So sediment in is equal to what's coming out from that location. However, once we disrupt that particular stream by implementing some man-made structures, then that equilibrium is broken. So we are moving into a different equilibrium where the incoming sediment amounts not fully transported downstream, but actually get settled within that specific structure. So sediment accumulation causes in the substructure over time loss in storage capacity. It reduces flood protection, loss in storage, navigation, recreation, as well as some other environmental effects and benefits. However, so when we built those dams and created reservoirs, we anticipated that to happen. So it's not an unexpected consequence of that. So even in the Reservoir Sedimentation Handbook, it says the structures are designed and operated to continuously trap sediment. So the issues that we are having are actually planned and anticipated. So how can we control or how can we deal with those issues? And we heard about 4 R's, and that's basically a summary of those 4 R's in a different context. So we can control sediment deposition by maybe routing sediment beyond the storage pool. We can remove deposited sediment on the reservoir by dredging or doing some other activities. Or we can try to reduce, maybe not completely eliminate, but reduce sediment inflow from areas upstream of the reservoir. So, and that's the last part of it is what I'm going to talk about today. So if you look at the upstream sediment sources, they're usually divided into several components or several parts. When rainfall drops, or droplets of rain hit the surface, so they create splash erosion. That energy of the rainfall drops basically dislodges soil particles that they become available to move with water downslope. So that moves into real and into the sheet erosion, and then real and interior erosion further downslope, where basically water follows the hill slopes and picks up energy and becomes more and more damaging to the land. So when it travels downslope, it converges into depressional areas and creates concentrated flow channels. So those becomes ephemeral gullies that can be removed by tillage or by some other ways of doing it. But eventually, if they're not treated, downslope, they're progressing into classical gullies. And those gullies are bigger channels that cannot be removed by simple tillage. And in that case, some specific mitigation efforts need to be applied. So when water and sediment moves into the streams, then we can deal with stream bank and stream bed type of erosion. So in my talk today, I am not focusing on gully or channelized flows or stream banks. So I strictly focusing on real sheet, real and interior erosion. And we'll discuss efforts that we've done using computer models of estimating amount of sediment that's moved with water downslope. So again, kind of like to repeat what I just said, so there are two distinct processes that usually defined in modeling of sediment transport. First, it's amount of soil detachment by the energy of moving water in the system, and the transport capacity or availability of water to transport sediment further downslope. So these two particular forces are in conflict with each other. So soil detachment and transport capacity of stream becomes a driving force basically for modeling efforts. If we draw a gradient, let's say a line from the uphill to downhill point on the landscape, then we can kind of like set up areas where we have depositional sediment and where we have areas of soil erosion. So usually more slope, more erosion, lower slope, or especially if you go into low slope area from the high slope area or steep areas, then you have more depositional parts of the landscape. In the erodible part of the landscape, sediment transport capacity always exceeds sediment load. So there is additional, the hungry water, that's what we talk about when dam is built and then 90% of sediment is trapped. So we have hungry water basically moving downstream of the dam, and that creates additional issues because in that case erosion is elevated and magnified since there is a lot of more room and water basically for sediment to be picked up. So when we go into the depositional area, so transport capacity is lower than the sediment load, so that extra sediment need to be settled. So and always we have this kind of like areas where soil eroded and where sediment is deposited on the landscape. Different factors, why is it happening? So if you have a simple uniform slope without any changes in the gradient, so in that case, most likely all sediment that's been detached gets deposited all the way down to the stream. If we have some more complex landscapes, then we have different areas of deposition and erosion. In addition to that, if we have man-made alterations to the landscape, then we have this increased opportunity for sediment to settle within the channel or within this hill slope. So those are more complex cases that's kind of like described in a couple more images on this slide. So this brings me to the outline of my presentation where I'm sorry, I'm just hitting this button. It's kind of like integrated into the main key and so on. So anyhow, my outline, so in my presentation, I will talk about several models. And so those models have unique purpose. So they have different physical underlinings, and also they have different scale where they can be applied. So I will start with like backwards. I start with large-scale modeling with the empirical model. Then I move into the watershed or catchment scale modeling with more process-based model, and then end up with a hill slope scale modeling with a physically based model. So once we go through all of these modeling efforts, so we look into how we can regionalize some of the applications of our smaller scale analysis for the state of Kansas or regionally in Midwest. Okay, so the first model that I wanted to show, and many of you know it already, it's called the USLE, Universal Soil Loss Equation Model. It's basically a product of 5 factors related to the main driving forces for soil erosion on the landscape, such as runoff, soil erodibility or soil properties, then topographic properties of the landscape, which are slope length and slope steepness. And then we go into more land cover and land use, which is C and P factors. So once we know the values of those factors, we can multiply them and calculate the soil loss. That's the underlying principle of the soil loss equation. So it's simple in its nature. However, each factor may have a complex equation associated with it, but at the end, it's a relatively simple formula that's widespread on many models and many applications, including NRCS's way of estimating soil erodibility on producers' fields. So USLA was originally designed in 1965, and then had a couple more iterations of updates and so on. The latest is called Russell 2. Then they split it into more raster-based rather than the field-based model, and so on. But it's still in use heavily by NRCS. So the beauty of that model in its simplicity. And with the tools that we have now, we can utilize remote sensing data sets to calculate those soil losses almost in no time. So like we open Google Maps and we zoom in and we can see the landscape. The same way with this specific engine, which called Google Earth Engine, we can basically automate the process of collecting those specific factors. So at the end, what we can get is basically a map of each individual factor or map of the soil loss. Yes, it may not be empirical, so it may not be extremely accurate, but that's split into individual kind of categories of low soil erosion, medium soil erosion, high soil erosion areas is extremely visible and can be used in management strategies, in planning, and so on. So the map is produced, let's say, at a 30-meter grid cell. So even within an individual field, you have some variability of soil erosion. It may not be exactly accurate when we zoom into a specific field. However, in general, it will produce us long-term estimates of soil erodibility, of soil erosion and sediment production on that particular field. So advantages of this method, again, it's simple, it's empirical in nature. At the same time, it has certain parameters that describe the system, and it's easily integrated with geospatial and web-based tools and can be used for management decision making. So however, there are certain limitations in it. Of course, it doesn't transport sediment from one point to another point. It's empirical in nature which is again simplification of it. And it has specific spatial and temporal constraint. You cannot use this model for today, for tomorrow, on daily estimate. It's a long-term estimate of specific conditions on the land related to soil erosion. And of course, it excludes majority of the processes, physical processes that may impact this output. So the second model that we use, and we used heavily this model for all these 319 projects, 9 element plans and so on, it's called SWAT, Soil and Water Assessment Tool, that a little bit more physically grounded. It also splits the region or area or watershed into specific field units. Each of them has like unique properties of soil, land use, topography, and so on. But it also allows you to route the flow. So flow from the upper areas can be semi-routed to the downslope areas and into the stream and so on. It also allows us to do simulations on the daily time steps. So we can estimate moving forward basically how much soil erosion could be produced for specific rainfall events. So however, it's still not fully physically based, and it has some certain limitation from how the landscape is described or implemented in this model. But we are again going through all the steps of building the model, going from the collection of data sets, including remote sensing data sets, then putting it all into the GIS model, working with this GIS software, and so on. But then once we are able to generate daily outputs, let's say, or monthly outputs, so we do need to calibrate the model. So that step becomes extremely important, otherwise model is not realistic. But after all of these 3 main steps are done, then we can go into analysis of the results and estimating erodibility of the soil. So one example I'm showing here related to the Little Ark watershed that we just finished. Basically, it's a watershed upstream of the city of Wichita. And this particular study related to the offsite BMP program, where urban implementation of BMPs were replaced or offset by BMPs in the rural areas, and so on. So we did a comprehensive model development and model calibrations at several locations within the watershed. And at the end, we did produce a map of, at the field scale, of potential sediment rates or soil erosion or sedimentation rates. So once the model is built with actual conditions, so now we can run multiple scenarios, look at the BMPs and how much sediment can be saved and so on. So one particular example or exercise that we had with this particular model is that we wanted to find most producing fields that make sense to us to implement BMP on, that give us about 200 tons of savings of sediment per year. So those graphs that's presented here that look at the conventional tillage, and we planted corn for this scenario everywhere. And we look to other BMP-related scenarios where we have no till implemented on all the fields and no till with cover crop on, again, all the fields. So we can see that overall, so we had significant reduction in sediment based on this artificial, relatively experimental scenarios. However, the one bigger output that we were able to extract is basically analyzing sediment production at the field scale in the whole watershed. So not all fields made equal. So some of them produce more, some of them produce less. And of course, we wanted to implement the practices where sediment is heavily skewed in the production, rather than other fields where it's not. However, it's not always possible, and one of the studies that we did in the past is that human factor and social interactions create more issues to implementing BMP than this exercise or experiments that we do on the computer. But overall, so we were able to apply cluster analysis, identify patches of fields and specific subbasins where sediment is heavily produced. So that spatial targeting reduce BMP implementation or reduce the area, but increase basically our savings from the sediment standpoint. So at the end, we were able to find specific areas and specific fields that can be targeted for the BMP implementation. Again, it's a hydrologically consistent model, spatially distributed, relatively flexible in the setup, and can be built these days with GIS tools, relatively inexpensive. So however, still there is no in-field routing within the area. Calibration takes a lot of time and effort, and again, ephemeral and gully erosion is not simulated. So that brings me to the last model that I wanted to show, and it's a USDA-based model. It's called Water Erosion Prediction Projects. It's not a new model. It's been under development since the 90s. However, the good thing about the model is that it looks at the physically based processes of sediment detachment as well as transport of sediment. So one limitation of the model is that you need to create a hill slope area and identify the most preferential flow path. So it's not a two-dimensional model. It's not a single lumped area model. It's a flow path model. So if we, hold on a second. I'm moving in the wrong direction. Am I? Okay, I'm not done yet. Can you help me? Yeah. Go back to the web model. I don't know. Oh, there is a button at the. Okay, I'm. Yeah. Okay. So one example that we worked on recently is, again, related to that Little Ark watershed up north of the city of Wichita, specifically in the Running Turkey watershed. It's a HAC 12 area that had average slope of about 1% or so, and majority of soils on type C and D, but it's heavily agricultural production area. So since the model, it's a small scale, kind of like a field scale or even subfield scale model, then you need to generate an area, that hill slope area for the output for the model to be generated. So what we did basically, we took that 20,000 acre area and using specific GIS tools with a lot of elements according to it. So we created 6,000 small channels or small preferential pathways in the area that has these unique and strict conditions that correspond to the sheet and reel erosion processes. So we try to eliminate processes related to channelized flows as well as those little tiny areas where erosion may not be present at all. So this is an overview and kind of like representative one section of the land with, I don't know, more than 100 individual smaller sub-web areas developed for it. So for each of the sub-areas, so we identified the flow path, we had slope calculated and embedded or included in the model. So we added soil type, and we also looked at multiple years of land cover from National Agricultural Statistics Service to create those dominant crop rotations. So all of those individual steps were done and put into all these 6,000 individual models, and at the end, we generated a collection of the outputs from this model related to different, again, years where corn or soybean or sorghum or winter wheat were growing. So for each of that collection, we also split those 6,000 models into conventional till, no-till, and no-till and cover crop. So at the end, we saw the differences and we saw the changes in the distribution of the sediment or soil erosion in that particular watershed, which gave us, again, the basis to do additional analysis related to finding the specific places where soil erosion is more heavily present on the landscape. And we can see how blue distribution represents the baseline, which is the conventional tillage, and when we move into more BMPs, we shift it into the lower values of the sediment output. So one particular effort that we are doing right now is basically we're trying to use this subset of outputs to expand or extend it to the whole Kansas. So realistically, we cannot model, if you model 6,000 for one HAC12, and we have 700 of them, of HAC12s on the eastern part of Kansas, so it's realistically difficult and time-consuming to model all of them. So we're trying to use machine learning approaches to basically generate these models based on selected HAC12s and expand it to the whole Kansas area. So again, physically based approaches are good, although they're really time-consuming and computing intensive. However, we are able within the channel and within the specific hill slope to identify areas of soil erosion and soil deposition and sediment deposition. So kind of like disadvantages of that model that it can be easily applied to one HAC12, but on the regional scale it's difficult. And if you want to build upon the model, so nutrient and some other processes are not included as of now in this specific version of the model, although all of it in the development. So what I wanted to move next, kind of like we have those three individual models that can work really nicely on different scales, but how do we use it to provide realistically accurate or relatively accurate outputs as a regional scale? So one effort that we are conducting right now is collaborating with Iowa State University and developing this kind of like a daily outputs of soil erosion calculated on average at HAC12 scale. So this is an example that's done for Iowa, but it's the same. Similar animation can be done for Kansas as well. So if you look at Kansas right now, so we have 744 HAC12s included in this model, which covers about 31,000 square mile area, and almost all the eastern part of the states, including part of north central area as well. And if you see the map where this product is called Daily Erosion Project, is covering the estimates. It's again almost all Minnesota, Iowa, and Nebraska, and we are moving into Kansas with a new project, not a new, but with a recent project with Kansas Water Office. So within each HAC12, instead of modeling all 6,000 that we did in our small test study, so we're using up to 100 to 150 representative hill slope using stratified random sample selection approach of all of that. Significant effort also was put into developing these daily estimates of land use condition, of plant growth stages, and so on. So even rainfall is collected automatically as a 15-minute time step and then expanded for daily calculations within each hill slope. So right now, the model produces estimates at 6 a.m. for the previous day. And you can keep looking at those on the website, looking at the long-term assessment of soil erosion or short-term indication of soil erosion rate. So again, the model uses kind of like a multiple set of remote sensing input data set as well as inputted physically based conditions and plant growth conditions in the area. For Kansas, that's what we have right now. So that area in the middle, that's where we're moving in, and then we'll be next moving south central portion of the state. So western part of the state may be covered once the wind erosion component of the same model will be added into the model. So one example for, again, the same Turkey Creek watershed. So we can see that monthly averages of precipitation, surface runoff, soil losses, and sediment delivery are presented in those graphs, and you can download that from the website, as well as you can download daily values. And I just, for illustrative purposes, generated kind of like a map, a sediment rating curve map, relating sediment output versus at the for daily runoff events versus daily runoff values, and we can see that it's a nice power function as it's supposed to be based on all knowledge. As a sibling project that we also involved in is we're developing a dashboard, again, it's a HAC-12 scale right now, where basically you can go and you can immediately look at different impact of different tillage practices, as well as the next stage will be impact of different BMPs and plant types. That's mapped within HAC-12 scale output. So overall, this is kind of conclusions to my talk is that reservoirs are critical structures, and we build them with purpose. However, they fill with sediments, so integrative approach to management of water and sediment is extremely important for long-term sustainability of the reservoirs. So, and different scales provide different level of assessments, and we need to be careful which model to use to evaluate those practices. So at the end, daily erosion project that we are coordinating with Iowa State University can provide an assessment of soil erosion at the regional scale, and hoping that outputs that will be produced will be beneficial for future management and practical usages in the state. So with this, thank you very much. I again acknowledge my collaborators in the department, outside of the departments, outside of the state, and so on, even outside of the country, for this work. And with this, I will take any questions. Let's say the last model, web model, it's physically based, so it uses detailed soil properties, soil erodibility properties. So we do take values from Sergo, but it's not a direct input. That's a raw input into the model. So then within the model, those values are updated based on the cover, based on the management practices, based on the runoff conditions. So it's Sergo, but it's updated, and that's developers of the web model. They have more details in how it is done, but basically it's a little bit step ahead, step forward, step up, let's say, from the Sergo data. That's excellent question. That's basically what takes the most time to build the model, is to properly calibrate it. Because we're building it with default values that's provided black box kind of like approach. So we use multi-step calibration for different models. So let's say SWOT model is the one that's used heavily for soil erosion assessment, hydrological modeling, and so on. So you can do two types of calibration and validation. So one of them could be at the stream level, another one is available at the field level. So stream level is USGS or KGHE provided some water quality-based assessment or some sampling data and so on. Since the model produces daily outputs and we took actual precipitation and climate data, then the output should reflect what we measured in the stream. So what we do, we basically look at the point where the USGS station, let's say, is located, and we take output from the model and compare day to day with what USGS measures. So at the end, we tweak the model in a certain way to make sure that our conditions or our output. So that's at the stream level. So when we go into hydrological, like stream flow calibration, then go sediment calibration, total sediment, TSF, and then we go into the nutrient calibration, because each of them depends on the previous calibration attempt. So if you look at the field-based calibration, this is a little bit tricky because you don't have any data unless you put your own distance sampler or something like this at the edge of the field. Even in that case, it's pretty questionable. So what we do kind of like a vegetation-based calibration. So model has a plant growth included in it. So what we use these days NDVI and some estimates of the production of vegetation biomass. So we use model output for the same area and compare it with the remote sensing output that we can collect as well. So that's kind of like the best way we can do at this point for that watershed scale analysis. Yes and no. So yeah, we can. So for this simulation, we had two types of cover crop. So one of them was winter wheat. So we used winter wheat as a cover crop, but we killed it basically in May and not let it grow all the way until it harvested. So it wasn't harvested; it was killed. So and then there was another one that was like included mix of or whatever the model had as an optional for us. We are doing another study right now more on the western Kansas with a different model where we have a really specific types of cover crops implemented in the model. And we are at the mercy, honestly. So cover crop, you may not have all the plant-based parameters within the model identified for really unique combinations of those crops and species and so on. So we're trying to find, looking at the plant databases and